Today's video, we are going over chemical structures. We're looking at covalent and ionic bonds, and we're going to be using Lewis dot structures to figure out how these compounds and atoms combine together. Now, before we get into that, I want to highlight one quick thing as to why we're even learning organic chemistry. Organic chemistry is everywhere. In fact, right there at your desk or wherever you are watching this video, you can look and find organic substances. That's kind of weird, right? But it's true. So for say example, my stylus pen here has a plastic on it. Plastics are made from organic chemistry, the knowledge of organic chemistry to make polymers. Food science, very driven by organic chemistry. I need protein, and so I like to put it in my smoothie. And thank goodness for organic chemistry that makes it taste like vanilla. Don't believe me? Look at the back on the ingredients. It says natural and artificial flavoring. What is that artificial flavoring? It's a specific organic compound that tricks your tongue and your brain into thinking it's vanilla. I don't mind. I get my protein and it tastes great. Cosmetology is another area that organic chemistry is used a lot in. You know what? Actually, my hands are kind of dry. Lotions. Look at the back of one of your lotion bottles. You can actually start to look up some of these compounds like stearic acid or glycerin. And these are all of the knowledge that we have about organic compounds comes from organic chemistry. In this course, we're going to first look at how we can even build these large compounds, and then we're going to learn about their reactivity. It's all based on fundamentals. So stick with me as we learn the fundamentals. Okay, and then we're going to build upon it with each new idea. Let's dive in now to different types of bonds. We have ionic bonds and covalent bonds. Now, ionic bonds are ones that the electrons are not shared between the two atoms. And these have a huge difference in the electronegativity. Hi, Rhodey. They're dominated by electrostatic attraction. That's right, Rhodey. They're also soluble in polar protic solvents like water. Think about something like sodium chloride, right? Table salt. Table salt also includes some potassium iodide. Iodide is a micronutrient that we all need. It's also anti-caking, so that way when you start to shake it on your food, it comes out fine. So sodium chloride is an example of an ionic compound where the sodium has a positive charge and the chlorine here has a negative charge. Another type of bond is a covalent bond. Covalent bonds are when two atoms share electrons. They usually have a small difference in electronegativity. Say, for example, methane. The carbon and hydrogen here have a very small difference in electronegativity that we'll talk about in this video. This is really where we build the most complex molecules. They're not relying solely on these electrostatic interactions. They are sharing electrons to make new bonds. And this is where we can get really crazy and draw structures that are much more complex because of these covalent bonds. Let's dive in here and look at the periodic table and remind ourselves about the trend in which atoms are the most electronegative. As you go up and to the right in the periodic table, that's where electronegativity increases, where fluorine is the most electronegative atom. Now, what about these guys? These are noble gases. These all have octets, where there are 8 electrons, or in the case of helium, there's only 2. The outer shell is full. The outer shell is completely full, and these are the most stable. The reason this trend exists is because all of the atoms are kind of trying to get to be like the noble gases. So if we take, for example, lithium, this lithium fluoride, and again, like I said earlier, fluorine is the most electronegative. In order to form an ionic bond, you essentially need to transfer an electron. So typically what will happen are elements here in groups 1 and 2 are most likely to form ionic compounds. If they lose electrons, they'll be able to have the configuration of their corresponding noble gas. So let's take, for example, lithium fluoride. Lithium has one electron in its valence shell. And the easiest way to tell this is to look at the group number. Here's lithium, and it's in group 1. That's telling us there's one valence electron. This is happy to get rid of an electron, which will have the helium electron configuration. Let's take now fluorine. How many electrons are in the valence shell of fluorine? Well, we go over to fluorine over here. It's in group 7. That means we have 2, 4, 6, and 7. Notice here that when you draw the Lewis dot structures, you're always pairing as many of the electrons as you can. So there's 2 on each side of the atom. Fluorine, on the other hand, would love to gain an electron. Because this configuration is very similar to neon. Now it has its full octet if it gains an electron. This is why lithium fluoride exists as an ionic compound, because lithium can transfer an electron and give one to fluorine. So what you'll have here is you'll have a lithium plus and a fluorine minus. There's a few different ways you can draw these Lewis structures. So you could draw it like this. The fluorine, drawing in all of our electrons. You can also draw lithium fluoride like this. This is assumed to have both the negative and the positive charge, and it's shown here as neutral because they do cancel each other out. You could also show it like this. However, drawing a single bond between the lithium and the fluorine is actually frowned upon. So this is kind of signaling to other chemists that this is a covalent bond, which is what we know is not there. So when you deal with ionic bonds, you typically will show it either both charged or the Lewis dot structure, or just simply draw it neutral if you have both a negative and a positive. Let's now dive into covalent bonds. So we're going to draw the Lewis dot structure of methane. First, we need to look at what we have. So we've got CH4. How do we know how many valence electrons are in carbon? Well, we look at the group number. So here's carbon, and it's in group 4. So that means that we have 4 valence electrons. So I'm just going to draw carbon with 4 electrons here. We have 4 hydrogens. And we know that hydrogen, which is here in group 1, will each have an electron. As we draw this Lewis dot structure, we're going to see that each of the hydrogens can make a new covalent bond with one of the electrons in the carbon. So essentially what we're going to do, we can draw our carbon here, and then we're going to buddy it up with a hydrogen. Now, if I were to separate these electrons, you would see that if I draw the hydrogens in green, you will see that each of the bonds contain 1 electron from carbon and 1 electron from hydrogen. This Lewis dot structure is perfectly fine to draw for methane. You could also draw it using single bonds. So in this case, if you have 2 electrons that are signifying a covalent bond, this is equal to simply drawing out a single line showing that there's a covalent bond. Now keep in mind, this is methane and I haven't shown its 3D structure like I did on the first slide, but simply showing you what the Lewis dot structure looks like and also is acceptable to draw. Either way is fine to draw this. Let's now talk about formal charges. These are extremely important, especially when we're dealing with organic compounds. It helps us decide what's going to happen with the reactivity. Here I have a partial of our periodic table. What I want to do is first denote how many bonds each of these elements have in order to have no charge. So the bonds needed to have no formal charge. Well, if we look at hydrogen, we know it has 1 electron. So simply having 1 bond would make it neutral. So this is in line with the group number, which is also 1. If we go over to beryllium, it's also 2, okay? Boron has 3 electrons in its valence shell, so having 3 bonds would make this neutral and happy. Carbon, on the other hand, has 4 valence electrons, and we typically see carbon making 4 bonds. Again, no formal charge if there's 4 bonds on carbon. Now we start to get a little tricky. For nitrogen, it's 3. Nitrogen has 5 electrons in its valence shell. So what's going to happen is there will be 1 lone pair and 3 bonds. For oxygen, it has 6 electrons in its valence shell. So what will happen here is that we will have 2 bonds and 2 lone pairs. Last but not least is fluorine, where it's happy with 1 bond, okay, 1 covalent bond, and it's going to have 3 lone pairs, which add up to its 7 valence electrons. Now, a topic we need to talk about here is the octet rule. Elements like to have 8 electrons in their outer valence shell. When we looked at the case of methane, the carbon here has 8 electrons around it. Now, when you are talking about the octet rule, you do add in any shared electrons. Each bond will correspond to 2 electrons. So, for example, if we had hydrogen fluoride, HF, if I draw in my lone pairs on fluorine, I would have 2, 4, 6 electrons in my lone pairs, and then 2 additional electrons here from the single bond, because one of the electrons from hydrogen is being shared. So this does, in fact, satisfy the octet rule. Now, nitrogen, oxygen, and fluorine, these groups here must follow octet rule. Let's do an example together. Let's do ammonium. So here we have NH4+. Formal charge is calculated by the group number minus the electron count. So in this case, our formal charge is +1, and nitrogen, we know, has a group number of 5. So 5 minus the electron count. This is going to be around our nitrogen. This means that our electron count has to be 4 for this compound, which makes sense if we look at this. So here's our nitrogen, and we have 4 hydrogens around it, each of which are bringing in 1 electron because hydrogen is in group 1. Nitrogen then would have 4 electrons, and each contributing to 1 covalent bond. This is the same as having these 4 single bonds drawn like this. You can always double check your work by looking at the nitrogen, seeing that it's in group 5, and then counting the number of electrons. Now notice this is different than when we look at the octet rule. The octet rule combines the electrons in covalent bonds. Covalent bonds equal 2 electrons. The octet rule says, I don't mind if you're sharing anything, I just need to know that you have 8 around you. On the other hand, for formal charge, this is a tactic for us to describe the electronics around this atom. They're not always true, and we'll get into that in a minute, but it's a note-taking skill of how we can keep track of the electrons. So in this case, what you do is that you only count the electrons that are coming from the atom you are looking at. So in this case, because we're looking at the nitrogen, we're only looking at the electrons that came from the nitrogen. So in each of the bonds, only 1 electron is coming from nitrogen. So in this case, our group number here is 5. There are 4 covalent bonds. Each have 1 electron from the nitrogen, so it gives us this +1 formal charge. And so that's how you would use your Lewis structures and figure out the formal charges of compounds. Let's do some practice problems together. So here we have H3O+. So we've got a hydrogen, a hydrogen, a hydrogen, and an oxygen. And we know that oxygen has 6 electrons. Because the formal charge is positive, this means that one of the electrons in our oxygen are no longer there. So essentially, you would just erase one of your electrons. So now we have 5 electrons for the oxygen. So now we can start to piece together this compound. Each hydrogen is providing 1 electron. Let me draw the hydrogens here in green and the electron that's corresponding to it. Okay. And then our oxygen here, we said had 5 electrons, so it should have a lone pair. You could also draw this structure with the single bonds and having 1 electron pair. You can double check your work and you say oxygen has a group number of 6. And if I count the electrons, I have 2 from the lone pair and 1 from each of the single covalent bonds. So 2, 3, 4, 5. So this is 2 electrons here, and then each one of these would be adding up to 1. So that would be 6 minus 5 gives us our positive 1 for our formal charge. Let's do OH minus. Well, here we've got hydrogen, and oxygen we know has 6 electrons, but we have a negative charge here. So we're going to add 1 more electron to our oxygen. So now as I start to draw this compound out, let me draw my hydrogen here in green. You see that we do in fact make a covalent bond with our hydrogen, and we can redraw it, showing the bond of those 2 electrons that are shared right here as a single bond. And so we can now double check our formal charge here. Oxygen is in group 6. There are 2, 4, 6 electrons coming from the lone pairs. And there is 1 electron coming from that covalent bond. So 6 minus 7 equals a negative 1. And that's in fact what the formal charge of hydroxide is. It's just simply a base. So now we've taken Lewis dot structures and then looked at how we can assign formal charges. Now, the next step that we need to do is we need to understand whether or not these formal charges are actually telling us anything of real chemical importance. This is simply a note-taking tool of where are the electrons, but in some cases, the chemical reactivity is not described by the formal charge. Let me show you an example. We looked previously at ammonium, right? Let's draw that out again. So we've got nitrogen. We have 4 bonds to our hydrogen. And our nitrogen should have 5 electrons around it. It's in group 5, but it only has 4 here. That's where we have a positive charge. The way that we can decide if this is actually how the electron structure looks is we can look at electronegativity. So let's look here at the electronegativity values. If we find nitrogen, nitrogen has electronegativity of around 3. The scale goes up to 4 for the highest. And if we find hydrogen, it has an electronegativity of 2.1. So nitrogen is more electronegative than hydrogen. That means that the nitrogen is going to want more electrons. Well, if we go back to what we drew, the nitrogen here has a positive charge. So this really isn't telling us chemically what's going on. Actually, what's happening is we can draw what's called a vector for this dipole moment. So it's simply an arrow showing where electrons are actually going in the molecule, okay? So it's like, well, actually this nitrogen here is trying to hold on to those electrons. And so although the hydrogen and nitrogen are sharing with this covalent bond, it's not sharing evenly. Nitrogen's being such a hog. So when we redraw this, really the way that this reacts is that our hydrogens here on the outside are actually partially positive. Now you would draw this with the formal charge shown on the nitrogen, but understand that because of the difference in electronegativity, it's going to react where the hydrogens are actually acting as this partially positive element, all right? So let's test your knowledge here. Describe the bond polarity of H3O+. So first on your paper, you're going to draw out H3O+ like we did before, and then I want you to look at the electronegativity difference between oxygen and hydrogen and decide, where does that partial positive charge lie? Is it on the oxygen or is it on the protons? So go ahead and pause the video and give it a try. All right, let's go over it together and see how you did. So we have H3O+, a lone pair, and here's our positive charge. Now, the electronegativity of oxygen is around 3.5, and the electronegativity of hydrogen is around 2.1. This means that the oxygen is going to be pulling electron density toward it. And so really the way that this looks is that these hydrogens are partially positive. And they react in such a way. And so this is helping us determine that although the formal charge is keeping track of our electrons in the molecule as a whole, we do need to consider the electronegativity of the bonds to decide where these electrons are really lying in the molecule. As we keep talking about molecular structures, you'll see that there are times we'll draw things very simply on a piece of paper, but they are not that simple. They are full of orbitals and weird things happening with the electrons, and it's really our job to be able to draw it on a piece of paper, but also understand where the electrons are placed. So in this video, we talked about Lewis structures, formal charges, and we use electronegativity to describe molecules. And I'll see you in the next video.